So I'll start with the talk, and although it's not strictly mobile communication, I thought it was the right crowd because some of the community is also developing hardware, and USB-C is getting more and more popular, and maybe you want to switch to it. And this is how you develop hardware with USB-C and power delivery. And maybe in the end, you don't want to switch to USB-C, but that's up to you. At least you have the information. So first off, does this slide work? Yeah. What is USB-C? First of all, USB-C is just a connector. As we've seen already in mobile communication, you just start with letters A, B, and then comes C, like with the interfaces. Same with the cable. We had A for which we connected to the host, B which we connected to the device. Then, because it was too large, we had mini B. This was still too large and not reliable, so we had micro B, and now we have C, which kind of wants to do everything and nothing at the same time, or everything. So yeah, what is good, or what does Type-C want to do or want to fix? First, it wants to be reversible. So you can plug it upside down if you want, because micro USB didn't have it, and a lot of people were complaining. It wants to add charging, because USB in the beginning only supported 500 milliamps. USB 3 added up to 900 milliamps, and now you can even charge up to 240 watts with a Type-C, which is quite a lot. And by the way, ask questions whenever you want. Don't wait for the end if you have questions. And what else? Yeah, it supports USB, USB 3, USB 4, and alternate modes for example, HDMI, DisplayPort, or lots of other alternate modes. But USB-C does not have to support it. It can support it. So you can use USB-C without having USB at all. You can use USB-C without having power delivery. And you'll see why this happens, or how this can happen in this slide or in this presentation. And USB-C so it's yet another connector. So now we have a matrix of lots of connector. What can USB-C be connected to? USB-C can almost be connected to all other connectors, which we can see here. Only mini A and micro A are not standard anymore. Nobody wants them, and they're pretty rare. So everybody forgets them. But what this creates is a mess. Now when somebody asks me, I want a USB cable, I ask, yeah, which one? USB 2, USB 3, micro, mini, USB 3, and you have plenty of other things. And I think we will keep a lot of cables for a long time. USB-C will, in my mind, will not erase everything, because there's a lot of legacy and because it's complicated. So the USB-C connector looks like this in schematic, and you can already see how this can be reversible, because if you have the symmetry point in the center, when you reverse the A side to the B side, almost all connections are the same. You have 4 ground connections on the outer reach. You have 4 of them because they are smaller, so they can transfer a bit less energy. But also because with USB-C, you want to be able to transfer 240 watts. So you need a lot of connections. This is why you have 4 ground pins in this 24 connector and 4 V-bus pins, which are far from the ground pin, so it doesn't short immediately. Then we have in the center, in green, we have the D+, D- USB 2 lines. And you can also see that they are reversible, because if you just rotate it by 180 degrees, D- still becomes D-. From B7, it goes to A7. Same for the CC lines. We'll come to what CC lines are. So the configuration, channel configuration. The SPU lines also symmetrical. And then we have the super speed lines for USB 3 and other things, which are RX and TX2, which are not really symmetrical. So for that, you have to know which direction the connection is flipped. The technique will be shown afterwards. But you see 24 pins, lots of different things which you can pass through it. None of them are mandatory. You can do whatever you want with the pins, almost. And now, if you want to develop some hardware, the easiest and probably the most common cable you have now is USB-A to USB-C. The standard defines what's inside here, and it's nothing more than USB cable. You have ground, you have V-bus, which is the power, then you have the data plus and data minus line, and that's all. So there's nothing new to it. Now, what is a bit different is you see that you only have one ground and one power wire. Although you have 4 connections, there's only one wire, and in the plug, the 4 connections are connected together for ground and power. And then for the USB, you only have the USB pins on A6 and A7. You don't have it on B6 and B7. And what it means that if you want to connect your hardware over USB, what you simply do is connect both sides of the connector to the microcontroller, and that's basically it. So you just connect A6 and B6, which are D plus, to the side, and A7 and B7, which is D minus, the data minus. And no matter which way the connector is flipped, you will always have USB. The problem comes now if you have a USB-C to USB-C cable, because there you also have the problem that you only have USB on one side. And there is a new wire which they added, which is the CC wire configuration channel. There's also power Vcon, but we'll see somehow later in the end what it is. So for now, you can ignore it. The most important one is the CC line. Channel configuration. And what this is fun is that normally you are used, when you plug a USB cable, you immediately get power. Well, for USB-C, this is not the case anymore. When you plug a cable, you don't have power. You see here, I have an LED across V-bus and ground, and there was nothing until I've added this resistor. If I remove the resistor, I have no power between V-bus and V-ground. And if I add a resistor between one of the CC lines, this is just CC2, so one of the boost pins, and ground, then we have power. So this is the first tricky part when you want to create a USB device with a USB-C connector, is that instead of just having D plus and D minus, you will also add a resistor, which is called RD in the specification, and you connect it to ground. And because, again, you can flip the connector, you add it on both sides. So on A5 and on B5, you just add a pull-down resistor, and this allows you to power your device. Without that, you have no power over USB, over USB-C at least. And this is where already we see a lot of confusion is here. This connector has 24 pins. We don't use all the 24 pins. We just use the CC lines, the data lines, and the power lines. So because the connector is expensive, because you don't need all the time all the pins, you have various type of connectors, and they are denoted with the number of pins. You start with 6 pins. This is the one on the left. And on the 6 pins, it's only to power the device. So if you have something which is just battery operated and don't have any USB, just use this connector. You have power, ground, and the CC line, so you can enable the device. And over the CC line, you can speak power delivery to even have more power if you want. If you just have USB 2, then you need, starting with 10 pin, most common is 16 pins. You need one of these 16-pin connector, which are still surface mount, and on them you have 2 times the D plus, D minus lines. And then if you want USB 3 and other device and other things, you use this connector on the right, which has all 24 pins broken out, so you can access to all 24 pins. So that's the second step you have to think about when you have a device. Which connector do I want? Try to use the easiest one. Depends on your requirements, on USB requirements. What's also fun is this kind of cable, they exist. On one side, you have USB-C. On the other side, for example, you have micro USB. You could have also mini USB. They also exist, or just plain USB, USB-B, which is normally connected to the device, like printers and things like that. And if you look at the node 1, on the CC line, there is already a resistor embedded in the cable. So the 5.1 kilo ohm resistor, RD, is embedded in the cable. So the device which is using the micro USB connector has immediately power. But the CC line, the resistor, the pull-down resistor, is only on A5. It's not on both sides. It's only on one side because the host should detect if it's on side A, on side B, and determine the orientation. And how you detect the orientation of a cable and how you detect the orientation of a cable is explained right there. So what you do is you monitor, so the source is what you previously had at the host. So the source is the one which will deliver the power, at least in the beginning, and the sink will be the one which uses the power. So the source is most often your computer, and the sink is most often your device. USB allows you to swap roles, but we'll start with a simple configuration. We've seen that we have this RD connector, which is pulled low to ground, and this indicates that we want power. Now, the source will monitor on both CC lines the power, and it has a pull-up resistor, which is pulled up to V bus generally. And this pull-up resistor, if nothing is connected to the connector on the source side, then on the CC lines, the voltage is high. So it knows there's nothing connected, I don't have to deliver power. When a device will be connected to the CC line, the device will pull low this signal. And the source actually monitors the two CC points, and it will find out that one of the CC points is getting low, meaning now someone is getting connected, but only one of them. Just ignore RA for now, I'll explain later what it is. But because there's only one CC wire, this is VCon wire, it doesn't go from one end to the end to the other, to the cable, because this goes low, it knows exactly, okay, my CC line is on pin A5, or if it's here, it's on pin B5. And thanks to that, it knows the orientation. The sink can actually do exactly the same thing. It monitors both CC pins, and by default, it is pulled low by the RD resistor. And if you connect the cable to the source, then it will be pulled higher than 0 volts. And this way it knows, okay, now I'm connected to a source. I can ask for power, and the orientation of the plug is, so the A5 pin of the plug is actually on this CC line, is on this pin. And this is how you know how the cable is oriented. And we've seen that there is an RD resistor. This is fixed. This is 5.1 kilo ohm. But there is also a pull-up resistor. This is RP, and this can have several values. It really depends on what the source is capable of delivering in power. By default, so the default USB power is 500 milliamp for USB 2 and 800 milliamp for USB 3. This is one value. If you just use another resistor, for example, 22 kilo ohm, then you already indicate to the sink, you can draw up to 1.5 amp. If you put a 10 kilo ohm value, it indicates to the sink you can draw up to 3 amps. Now, you probably have heard that with USB you can draw up to 5 amps. Well, you don't do it using the RP value. You do it using power delivery. That's later on. So they've somehow added a new way to do it. Don't know why they could have just added a resistor. Maybe because they want to sell power delivery? I don't really know. But so yeah, you can have several RP values. And you already see this starts to get complicated. And this is just a USB 2 cable. So if you have a USB cable, a USB-C to USB-C, it doesn't mean that it can do USB 3. This one only does USB 2, and this is actually specified. There are USB 2 cables, which again have the data plus data minus line and the CC line. and shield, but they don't have all the other connections. This is a fully featured cable, so it looks exactly the same. It's probably a bit thicker, and it's probably a bit more stiff because you have a lot of other connections. And actually what they've added is these four pairs for the super speed signal for USB 3, USB 4, and other things. And then they've added also two single wires, which is for sideband use. These are alternate modes. If you do something else than USB, you can use these lines. But the problem is that you don't see from the outside, is this a USB 2 cable or is this a full feature cable with all the USB 3 lines? But the important first part was that you find out the detection, and on USB 3, these pins, the RX and TX pin, are not really swappable as you had with D plus and D minus. And also what they've changed is the name. We've seen previously that it's called D plus and D minus. With USB Type-C, it's called D positive and D negative. So if you see these symbols, don't be surprised. They just renamed it, probably because it fits better text. I don't know. And the same here, RX plus and RX minus. But RX plus and RX minus can't be mixed. So what you have here is a CC logic, which uses the CC1 and CC2 pins to figure out the orientation. And once it figures out the orientation, it will talk to this multiplexer or to this cross point, and it can map the right pairs of RX1 or RX2 and TX1 to the USB chipset if you want to do USB 3 or USB 4. So already with USB-C cable, you need two more components. You have your USB chipset like you had before, but you have a CC logic chip, and you have a multiplexer if you want to do USB 3. And if you think this was everything about the cable, no, cable is a bit more complicated. We have USB 2 cables, we have full-featured USB 3 generation 1, USB 3 generation 2, and then there's USB 4 generation 3. All of these cables, you have no idea what it really is just on the outside. But what is important in this slide is actually on the side, you see that you have electronically marked cable. So for cables which can carry up to 5 amp, it requires to be electronically marked. 3 amp doesn't require to be marked. They can be marked, generally they don't, but they can be marked. And this electronic chip is what I've mentioned with, is what I've hidden from you with the RA resistor. So in the cable itself, there can be a resistor called RA, and when this is present, it indicates that this is an electronically marked cable. And here what you see, what they call SOP, is actually the chip within the cable, which is there to, which is actually connected to the CC wire. And on the CC wire, this small chip can talk the power delivery protocol and can say, okay, now I'm an electronically marked cable, and I can source up to 5 amp. So you have to ask this chip over this line. And I've hidden from you, I've said that forget VCon for now. Well, VCon is there to power this electronically marked chip. So on both sides, you have kind of resistors. So you don't have an interconnection of VCon from both sides, but it can be used to power the chip within inside. And here in this schematic, there's only one electronically marked chip. You can have cables which are marked on both sides. So on either end, you can have a different chip. But yeah, so this is why, and VCon is used. So if you figured out this is the CC line which goes through the cable, what you have to provide if you want to use electronically marked, is that you provide a voltage to the other side. This is why it's called VCon, because you provide power for the chip within the cable. And so you don't only monitor for the RD or RP, you also monitor for this RA resistor. And the issue is that if you have cables, you have no idea, is this an electronically marked cable? Is this a USB 3 cable? Is this a 5M cable? You just don't know. So I've developed a small device which actually tests the cable. It can tell you if this is USB 2, if it has super speed lanes, the sideband use lanes, and if it has an E marker. E marker doesn't always mean it's 5 amps. You have to ask the chip inside if it's really 5 amp, but it's a strong indication. And is this, the link is not there? Well, let me unscroll this. Yeah, here. So if you want to have a look at the device, you can hear the sources if you want to build one. And it's quite useful to identify the cables. So we've seen that we will have a look at this part here, the logic. My device here is only to identify the cable. Once you have a cable, you also need on the device, so not on this one, but on USB device, you need this CC chip. And we'll have a look at this CC chip. This is how, so they are called Type C controller or Type C power delivery controller. And this is the functional diagram of one of them. FUSB 302 is a popular one. There are plenty of other ones which do it. And they are here to assist you with USB-C. We've seen they don't have a lot of connection. They have the connection to the microcontroller, and they manage all the things you want to do with the CC lines. So they are directly connected to CC1 and CC2. They're also connected to power. And here you have lots of switches, so you can do several things. For example, you can ask this chip, please connect it to RD, so pull down, so you can indicate that this is a device. You can also ask here, this switch here. This is actually a current source. This simulates the RP, so the pull-up resistor for the source. And here you can set, okay, I want to indicate that I'm a 3 amp source or 1.5 amp. So then you connect it here. Also, because you actually want to monitor what is on the CC line, because you want to detect when a source or a sink is connected, you actually have a digital to analog controller. So you actually connect the CC lines almost always to the digital to analog controller, and you monitor for the voltage changes. And in the chip itself, you can tell, so in this controller chip, you can tell that if this happens, then you should do that or just use this profile. Once you did the connection and you know one is for power delivery, you can also use VCon, which is just power, and you connect the power to one of the CC lines, so you can actually power the electronically marked cable. And the last one, which is this block on the bottom, so the BMC physical layer, this is to actually talk power delivery. And we'll have a look at the power delivery protocol now. So we've talked everything about the USB-C connector, and we'll switch to what power delivery is. So if anyone has questions about USB-C connector, or if it's not clear, let me know. Else, I will switch to power delivery. And yeah, it is power delivery complicated. No questions so far. Okay, so let's switch to power delivery. Power delivery, this is how it looks like on the electronic interface. You only have one line to communicate. Everyone talks on the same line, the CC line. How it is that nobody drives the line when they don't want to talk. And as soon as someone wants to talk, they drive it high or low. And high or low means 1.2 volts, so it's a very low voltage level. And anyone can talk. There is no master, no slave. Anyone can just start talking and send messages. The encoding is used to biphase mark coding. This is what you see here. This is why you often see BMC. BMC stands for biphase mark coding. And what it does is that at every new bit, it changes the voltage level. And if it's at 1, it changes in the middle of this data bit. If it's a 0, it doesn't change. And this is how they communicate it. So why did they use that? Actually, USB-C didn't invent or didn't have it's not the first time power delivery existed. Previously, it was existing already with USB-A connectors, but you had to encode it in VBus. And because of how the way you encoded it, they used the BMC encoding. And the bit rate of the bits is 300 kilobits, and this is fixed. You cannot change it. And 300 kilobits, that's okay as speed. It's not too fast, but again, it's just a protocol for power delivery to negotiate power. That's how on the electrical level it looks like. And if we have a look at the layer above, this is how a packet looks like. You have in the beginning, so nobody drives the line. There's only the resistors, so they might be noisy. So what you do in the beginning, you have a training sequence to actually indicate, okay, now I'm starting a power delivery packet. It's not just noise on the cable, it's really a packet. After the training, you have the start of packet or SOP. This is what you've seen in the electronically marked cable. SOP star means it can be any start of packet. And this indicates who you want to talk to. Do you want to talk between sink and source? Do you want to talk to the cable? And which end of the cable? And this is identified in the SOP packet. Then you have the message header, which tells what kind of packet it is. You have plenty of bytes. And because this is a wire where everyone can talk onto, you have a CRC, so a checksum, to actually detect, has anyone else been talking to meanwhile, because they didn't pay attention and they just started sending. If this is the case, the CRC will be corrupted. So this is a 32-bit CRC, the standard one, which most of the time you use. And you check if this is corrupted, it means that somebody else talked to it on the cable. And then the end of packet just to end the things. And to make everything more reliable, all the data bits are encoded using 4B, 5B. This means that 4 bits of data are encoded in 5 bits of these bits here. I think it's so you can recover the clock easier, because so the 4-bit 5 bits ensures that you have transitions frequent enough so you can recover the clock, so you can follow the data stream. I wonder if there's a USB version of USB kill. Yeah, maybe. It could be easier. You can actually, so I think you can actually have a devious cable which just asks the source now deliver 20 volts, and then if your device is not capable of having the 20 volts, then you can kill it. So now we talked about power delivery. What if you want to play with power delivery a tiny bit? Power delivery, as the name says, power delivery, it's most often used for chargers. If you just want to know, is my charger, so can my charger do power delivery and what kind of power they use? You can use USB power meters. And this is actually how I started playing with power delivery. This is the one I use, which is fine enough. It changed the name, but it's the U2. And so on the picture on the top, I've connected to a power delivery capable charger, and it can tell, well, I can do 5 volts, 9 volts, 12 volts, 20 volts. And what you see in the end, the 3 to 5 volts or the 3 to 11 volts, this is called PPS, Programmable Power Switch. So here you can set the voltage in 20 millivolts increments between 3 volts and 11 volts and up to 3 amperes. And then you can use the exact same device to actually check the identity of cables. So the small device which I've shown you with just LEDs, it just identifies, is it a USB 2, a USB 3 cable, and is it electronically marked? It doesn't actually test if it's really 5 amperes. And this small USB power meter asks the chip in the cable for the information. And the chip in the cable will tell you, I'm a USB 3 cable, I'm up to 2 meters long, and I can carry up to 5 amps. So you can use me for 400 watts charging, for example. Yeah, I also, if you want to play with the Web2, I also reverse the protocol actually. So you can have all the measurements from the protocol, being it over USB or over Bluetooth. Go somewhere on one of my on my Git, you will find it. And yeah, so that's okay. But this is really just so you don't directly play with power delivery because you cannot control the device. So the WebU2 doesn't allow you to actually see this data. It only allows you to read power, the current and voltages. So if you want to play with power delivery, this tool is not good enough. This is just to identify charger and cable. If you want to actually tap to the communication, what you can use is a level shifter. Now, you want to use a high impedance level shifter because you don't want to mess with resistor values if you connect your probes to it. So you have to one which has high impedance with op-amp, and you always have to, so you need a level shifter most of the time because it talks at 1.2 volts voltage level, and most logic analyzer go down to 1.8 volts, but most of the time it's 3.3 to 5 volts. But you can use here, this is how I started actually, sniffing power delivery. It's just two small level shifter and a logic analyzer because SIGROC, the open source tool for logic analyzing, has a power delivery analyzer. And this is actually the trace of the U2 power meter, which asks for the cable about this information. And we can see again the preamble. This is for the training. Then we have the start of packet, sub, and you can see sub prime. There's one little prime thingy, which says somebody wants to talk. So either it's for the cable or it's from the cable, both of the things. Then the header just saying, I'm a vendor message. And here in the first message, these are always 32-bit messages afterwards. So the header is 16 bits, and then you have 32-bit messages. And here it's a request for a discovery identity. And discover identity is just cable, tell me what you're capable of. Again, afterwards, you have the CRC, end of packet. And after every packet, so this is not the response to this request. After every packet, the other side has to ACK any packet with a good CRC. And this is just taking the sequence number from the previous packet and just, and in this header is just, okay, I got your message. This is just an ACK. This is not the reply yet. We'll have a look at the reply afterwards. And this whole message, because they wanted to keep the same format probably, has also a CRC. The problem with, or the limitation with SIGROC is that you cannot really decode all fields. So it gives a good indication for the header and the type of message, but not for all the bit fields. If you want to go deeper to power delivery analysis, I found this tool. This is the CY 4500 Easy Protocol Analyzer. And this does almost the same thing. It's just like a logic analyzer, but it does more because the software. So what I liked with this device is that you can trigger actually the oscilloscope. You have here this start of message pin and end of message pin. So if you want low-level debugging, then you can tap to these pins and then trigger your oscilloscope to it to have a look at the trace if something goes wrong or not. Then you have the two CC lines. These CC lines are still at 1.2 volts. They are not level shifted, so you cannot directly connect them to a logic analyzer. But this device also decodes it. And there is a software which also works on Linux. It's not open source anymore. Not this version, not the latest version, but it's quite good. It's okay. So this is what we see in the beginning. Again, we have 4 messages. We have the identity request. I've selected it. And we see that here we have the discover identity request. Then the second message is a good CRC. So it's the ACK. The third message is actually the cable replying to this identity request. We'll have a look at the reply afterwards. And so this is sent by the cable, and then the power meter will send that good CRC telling, okay, I received the response. If it doesn't receive a good CRC, then the cable should send this identity for a couple of times before it stops doing. So everything is defined in the specification. The USB specifications and power delivery specifications are freely downloadable on the USB forum, like you would any of the USB specifications. The problem with this is that neither the hardware nor the software are open source, but at least there is a good tool to do power delivery analysis. There is also, if you want open source hardware, there is also the Twinkie, which was made by Google at the beginning, and then you have two re-implementation, which is called Twonky and Fresh Twinkie. The problem with them, so they're open source, that's good. The problem with them is that they don't decode the message themselves. There's no software support. The only support there is for SIGROC to decode it, so it's still very limited. The other problem, so why can't we expand? Yeah, I'll come to expanding SIGROC. Wait just a bit. Yeah, we can expand SIGROC. Absolutely, we can. And but so yeah, you can use also this one to expand SIGROC. The problem with them is that there's no commercial distribution, and if you want to build one yourself, it uses a STM32 microcontroller, which, because of chip shortage, is not available anymore. And this is why I created my own device, which is called Power Delivery Trace. Like I created SIM Trace in the beginning, now I'm creating Power Delivery. With no commercial distribution mean that no one sells it on a store where no commercial distribution just mean no one sends it on a store. So I don't mean with commercial distribution that you cannot use them commercially. It's just that I haven't found a shop which sells these things. You can build them yourself, they are open source. It's just that the chips are not available. So the STM32, so the problem with the STM32 is that they're not available. This is why I created, so let's come to the PD trace. And this is kind of it's a different approach than the Twinkie, because on the PD trace, I use a microcontroller which is available, but I'm also not using just a logic analyzer. I'm actually using these Type-C power delivery controllers. We actually have two of them. And yeah, what I say here. So I do all the hardware handling, all the power delivery handling in hardware itself, and I'm relying on these hardware chips, which I use a bit everywhere. And then I'm connecting it to, so you can, the advantage of this device which I've created is that you can not only sniff the communication, which this device can do, and the Cypress one can do, but they are limited to, this one is limited to decoding. On this one, there is hardware support for sending, but there's not a lot of software support for that. With this one, it's a bit easier because I just use the power delivery controller, which does the sending. So it does correctly the power delivery message sending. So I can sniff messages, I can inject messages, and I can also set the R value. So RD to tell I'm a sink, RP to tell I'm a source, RA to tell that I'm an electronically marked cable. And with that, you can actually play with, you can play with that. And coming to why can't we expand PulseView? Yeah, you can expand PulseView. I decided to go the route to expand, actually to write a dissector for Wireshark, because there are more interfaces to Wireshark, and it's a very powerful tool to actually dissect all the messages. So I wrote a dissector for the power delivery protocol. It's not complete by far, but the basic things work. At least all the things I've encountered work. Important Yeah, so we will have a demo about the tool. While I set up the demo, you can have questions. And yeah, the picture, I write this picture because it shows you the mess that USB-C is. This is a USB-C hub. So on the connector on the bottom, it supports USB 2, USB 3, because it needs power, it has power delivery. It has also you have 2 USB ports, actually 3. So you have 2 normal USB ports like a normal hub. It also supports alternate mode. This is the HDMI protocol. And you can actually use this hub to power and to charge the laptop which is connected to the hub. So if you connect a power source to this connector, you charge it. This USB-C connector does only support power delivery. It does not support USB. On the other side, the USB-C connector on the side only supports USB. It does not support power delivery. So you have a huge mess with there. This is not really HDMI. This is so most of the time you find an HDMI connector, but this is DisplayPort. One of the alternate modes of USB-C is DisplayPort, and plenty of laptops actually support it. So inside this USB hub, there is a converter from DisplayPort to HDMI. So now it's time for a small demo. Here we have the interposer for the PD trace. We will start with, which will we start with? For example, here. Yeah. This is the USB power meter, which will ask for the messages, for the identity of the cable. So I will power it, and it is in the mode where it asks all the time for the identity. And you can already, using the tracer, you can already find out that it doesn't do everything it should do. So I've connected that. Let's switch to this one. And you can see here the request. This is the identity, the discover identity request. And you can see that this device actually asks for, do you receive UDP port or should we wrap it in GSM tab? For now, I just registered. I did not register a UDP port, but it uses a UDP port. It just uses this UDP port. I didn't integrate it in GSM tab because it has little to do with GSM, but it is still ongoing development and nothing is really registered, nothing is really published. So whatever works best, either we register UDP port or GSM tab, I don't mind using either way. So what you do, so generally what you should do is detect the USB cable with a chip inside by measuring the resistance. Here you see that this USB power meter is actually just stupid and asks on the CC1 and CC2 alternatively, and every second, are you a USB power delivery cable? And we can see here in Wireshark, this is the discover identity request. It doesn't do it properly. And we can already find out. And now, if I connect, so this is an electronically marked cable. And I mark it also because I want to know it. If I connect it, we see that the power meter detects it. And here you can actually see the messages, which are different. So it's always request, good CRC, this is the response, and then good CRC. And this is also what you see here. Discover identity, here's the, stop scrolling. Discover identity, here's the request. The cable responds with a good CRC. Then the cable sends the discover identity acknowledgement, which has actually the response. And the USB power meter responds with the good CRC, and then it does it periodically just to refresh. And if we have a look at the identity, it's mechanically mad, absolutely. If we have a look at the discover identity, we can see the information the UPM actually extracts and even more information. For example, we have a vendor identity, which is in the cable itself. And here it tells that this cable is USB-C to USB-C. it could tell that I'm USB-A to USB-C, but this is USB-C to USB-C. It tells that this is up to 2 meters, so 1 to 2 meters. It tells that this is capable of USB 3. Here we have the signals, and here, USB 3, Gen 1 and Gen 2. And then it tells that it is capable of carrying 5 amps. Is the vendor ID a normal USB vendor ID? I don't know. I don't know if it is or if it is registered anything. Probably yes, because it is a vendor ID, a USB vendor ID, and there is also another ID. So here standard or vendor ID, which is a bit different. So maybe it is standard, but I don't know. So this is how the Discover Identity request works and the response. Now we'll come back to the tool. Let's disconnect. Let's disconnect the USB power meter. And now we only have the trace with the interposer board and the electronically marked cable. And if I, for example, go to safe mode first, if I ask it to identify, am I disconnected? Why should I be? Connect again. If I say identify the resistor in the cable, you see that on the CC1 pin, there is this RA resistor. This tells us that this is an electronically marked cable. And the other pin is the pin which you can talk power delivery to. This is why all the messages were on the CC2 wire. And using that, you can actually even send, I can send discovery requests myself. So here we have no traffic anymore. I have no traffic anymore, and the USB power meter is not here, but then I can ask Discover Identity. And here we only see the response because the hardware is sending the messages itself. I don't completely have the decoded versions. It's just software which I need to write. But here we can see again the cable sending the good CRC and replying with the identity, Discover Identity. And the hardware takes care of replying to this message with a good CRC. Now, what's more interesting, so this is just the easy part. What's more interesting will be, for example, we will connect this. So this is the USB hub in the picture, and we will connect it. I have to say just monitor communication. Okay, should start monitoring. Now I'm connecting the phone to it this way, so you don't see what's on the phone. Here nothing should happen, and here we should see plenty of communication as soon as I connect to it. Let's clear this out. And we should see communication. So the phone detected that there's a device connected to it, and it will start sending the source capabilities. In the source capabilities, it tells the device what I'm allowed to do. Here it says I'm only allowed to send 5 volts up to 900 milliamps. And then the source can say, okay, I'm ready, I can send it to you. Here we have again the Discover Identity and discover other type of information about this USB hub. But the interesting part is when to this USB hub. So this is a USB hub, but now I can collect actually a USB charger. And this USB hub, which was previously a sink, will change role and will become a source, so a power source. Now, if I connect, the light change. And if we have a look here, we should see somewhere that there is here. We have a PR swap. PR means power role, because the device changed power role, and then afterwards, we see the identity, the source capabilities, which are now from the hub and not from the phone anymore. And here we can see that it is able to provide 9 volts, 12 volts, 15 volts, and 20 volts. And actually with you can go up to 48 volts. With Power Delivery revision 3, you can go up to 48 volts. 5 amps means 240 watts. And what that is done, so these are the capabilities. The sync, which is the phone, will request for position 1 of the source capabilities. And position 1 was always, so the first position is always the 5 volts. So now the charger will provide 5 volt up to 3 amps, and then the source says, okay, I'm ready. And this is how you change between source and sync. And using this tool, you can do, you could do everything. And that's basically it for the tool. For now, that's all I've debugged, actually, for all the demo I have. Is the PD forwarded relayed through the hub? Yes, it is. Can you talk to all PD-capable devices from anywhere? No, the hub decides, and the hub will tell if it forwards the messages or not. And actually, it's up to the hub to relay the messages. If the hub is not capable of handling 20 volts, it will not forward the 20 volts. It has its own, so it's not physically relayed. In the hub, there is a chip which reads the power delivery and which decides, do I now need, do I want to send the same capabilities or not? As far as I know, I didn't take apart this hub. Would be interesting to see if this is the case, because it needs to do the power role swapping. So I don't think it just no, I don't think it is connected electrically. I think it forwards the messages. So yeah, this hardware, so software is not, it works good enough for now, but it has still a bit of issues with the USB stack for getting all messages. And now if you want, most of the time you will, so if you develop with USB-C, you will have your own, let's come back here, you will have a CC logic. A lot of pain is that most of the CC chip come with a huge power delivery binary blob, which you can use from the USB chip to talk to it and to request for the powers and so on. So this is proprietary. It is huge. It takes a lot of space in the flash. So be aware, if you want to talk power delivery, take a chip with a bit more flash than you would think it is, because most of the vendors provide a large firmware. I don't use the one which is provided by the power delivery controller. I use the ROM from the Chromium OS. Chromium developed their own USB-C power delivery stack because they wanted to control the chip on it. They want to have all the firmwares open source on the chips, and I just reuse their stack. So this is open source. And because I only compile what I need, it shrinks a lot the size of this binary blob. Is it possible to encapsulate custom messages in PD? Yes, you can. You have vendor-defined messages where you can send whatever you want with it. Also, be aware, when you start to talk PD, don't look just at the revision 3 of power delivery. I think the current one is revision 3. Revision 3 is not backwards compatible to revision 2. You always need to have the two specifications in mind, because in the beginning of the trace, let's see here, I have any message here. You have always the indication I'm using revision 2, and this is a completely different stack than revision 3. The message encoding sometimes is the same, but it doesn't have to always be the same. And this also increases the huge stack of the power delivery. I have no idea why they don't make it just an upgrade. It's a complete separate stack. You can encapsulate absolutely custom messages in PD using vendor-defined messages. This is actually what we have in the Discover identity. The Discover identity is a vendor-defined message. This one is a Discover identity command. You can have proprietary messages. You even have firmware upgrade over power delivery, which allows you to upgrade the cable, or to upgrade any device which is not really a device which connects using a cable, but a device which is called a VPD, a Vcon powered device. So it acts just as a plug of a cable and not as a complete device. I have a cursed portable laptop which has 2 USB connectors, wired completely in parallel except for the CC wires. Yes, so if you have USB-C connectors, it doesn't mean that you have always CC wires, also CC wires completely parallel, or that you have power delivery. In the hub, one of the ports doesn't have power delivery at all. It has the CC lines to discover the orientation, but it doesn't speak power delivery. Don't try connect the charger with full-featured CC cable if you use a USB display port. Probably depend on the hub. Display. How can I check? Just in case. How you want to check? But use PD trace if you want to check. I don't know. Upgrade the cable. Yeah. Take a cable, upgrade the cable. Absolutely. You can upgrade the cable. And this cable only has 1 chip, but you can have cable with 2 chips, 1 on each side. This is also, if we look at, is it here in the Discover Identity? Here it says I'm an alternate mode adapter. This means that I'm supporting, for example, USB DisplayPort. This is described in here, if it supports DisplayPort or something like that. But you can have active cables where you can talk to, which actually switches the lines. For example, you can have an active cable which completely switches off the USB lines or the super speed lines or the SBU lines, either to switch them the right way around or to completely switch them on and have this USB cable used for something completely different than USB. So you have even USB cables with, so they are called active cables, which can mess around with the lines. And I think that was it. To have something else afterwards. No, so yeah, if you want to have a look at, the breakout board, the tester are open source, the power delivery is not ready. It is open source and you can find the code, but you'll have to wait a tiny bit. And I plan to, like SimTrace, to have it available to the Osmocom community using the Sysmocom shop. Still open source, but it will be available there once it is a bit more polished. So this is debug hardware. You see there are tons of pins which you don't require for not debugging. And if you still want to play, most of the USB Type-C controller speak I2C. So you can just use of this. They are QFN or BGA most of the time because they have to be really tiny. And you can actually re-implement that. Is any part of the exposed to the PC? Yes. Is any part of the PD protocol exposed on the PC via the hub controllers? Yes and no. It doesn't have to be. There are, so on my laptop, it is not. There are some laptops like on the Chromebook, Chromium OS, where it is. And actually, let me find the specification again, or the document I found about that, and I'll show you. Downloads, USB Type-C, and some don't do it here. If you look for this documentation, you can have access to the power delivery. I don't know to what class. I don't have a laptop which is able to do it. But you have SysFS access where you can actually talk yourself directly to the plugs. My stack doesn't have it. It's not mandatory. I think this is an Intel stack which they used. I don't know. So there are some laptops where you don't need this tool. You can actually use you can actually talk to the controller yourself, but this is quite rare. Yeah. Meanwhile, while the question is writing, if you look a tiny bit into power delivery, you will often find this acronym, TCPD. It stands for Type-C Port Controller. So this is the small chip which actually handles the switching and so on, the switching, which does all the detection. So it's a keyword you will often find. Get a full-featured cable, USB 2 only. Correct. Yeah. Actually, so I've presented the USB 2 cables and the full-featured cables. These are the ones which are specified. You have lots of things in between. I found cables, for example, magnetic cables, which don't allow power delivery to go through because they do their things themselves. They don't allow shields, so you have plenty of things in between. So it shows you how hard Type-C is. And something I didn't mention, if you start the receptacle for USB is around $1, €1. So it's still quite expensive, while micro USB, you get them for 5 cents. So, and because there have been 10 years of micro USB, most of the people have plenty of micro USB cables. So you can still rely for the next couple of years with micro USB, a chip connector, and an easy way to have USB for your microcontroller. Yes. So what uses have you seen on the SPU pins? Sideband use. I've seen 2 users. I've seen it in USB 4. For USB 4, you need these 2 wires, these SPU wires. The other one I've seen is audio. Often when you have a smartphone where you can plug kind of a converter to have USB-C to 3.5 millimeter jack, this is where it goes through. It uses the SPU pins. It uses sideband use pins. That's the only 2 I know of, but I haven't read the complete alternate mode specification. I wasn't too much interested in that. But yeah, I've seen it for USB 4. I think power delivery, DisplayPort also uses, but I'm not sure about that. And audio accessory uses them. And then on the sideband use, you have actually analog. You have analog signals going through the sideband use pins.